The idea of an EDTA titration being selective can be a difficult concept. So this is a problem that hopefully will demonstrate that concept to you. So we have in this case a mixture of iron 3 plus and calcium 2 plus. So the idea of something being selective is that if you have a very strong complex or something that can form a strong complex to EDTA, you don't need much EDTA in the deprotonated form. So it can be run at a low pH. Remember, EDTA is an acid, so at a low pH you don't get much of the deprotonated form present. So iron can form a very strong complex, so we can titrate it at low pH. Calcium, on the other hand, forms a weaker complex, so it needs more deprotonated EDTA to be present. So you have to run it at a higher pH. So at a low pH, at pH 2, we've just got iron titrating, iron forming a complex with EDTA. At pH 9, we have both iron and calcium. So what we want to do, first of all, is let's look at pH 2. So at pH 2, we just have the iron titrating. So we would do this as with a normal titration calculation. So we want to figure out the number of moles of EDTA. So that's 0.1 molar. It takes 10.13 milliliters, or 0.01013 liters of EDTA to get to the equivalence point. That's going to be 1.013 times 10 to the minus 3 moles of EDTA. We don't have to worry about equilibria or the fraction of EDTA in the deprotonated form or anything like that for this kind of calculation. And it's a 1-to-1 ratio always between EDTA and metal, so that's going to equal the number of moles of iron 3 plus. Remember, calcium cannot bond at this low pH. So to find the concentration, it doesn't say what units to use, but we'll use molarity. So to find concentration, we want to take the number of moles of iron and divide by the volume, which was 50 milliliters. And that will give us a concentration of 0.0203 molar for the iron 3 plus. Now we want to find the calcium. So we do a similar kind of calculation for the second aliquot. Aliquot just means portion. So the second portion run at pH 5. So pH 5 we have calcium and iron reacting. So we figure out the number of moles of EDTA, which in this case was 15.27 or 0.01527 liters. And that's going to give us 1.527 moles of EDTA. And that equals, so that's EDTA, that's equal to the sum of the moles of iron plus moles of calcium. So since we know moles of iron, we calculate that at pH 2. We can just subtract. So it's 1.527 times 10 to the minus 3 minus the number of moles of iron, which we worked out to be 1.013 times 10 to the minus 3, will give us moles of calcium, which is 0.514 times 10 to the minus 3. Divide that by the volume again, it's the same as before, it's 50 milliliters. And we'll get a concentration of calcium which is 0.0103 molar. Notice also that we have different indicators. So at pH 2 we have salicylic acid, at pH 9 we have area chrome black tea. So indicators are also pH sensitive, and they're also complexes specific for the particular type of metal. So they're also important when we talk about selectivity.